Every piece of novel information you encounter must pass through a strict biological bottleneck before it can be learned. Human cognitive architecture requires that all new, unfamiliar data be actively processed in what we call working memory, a system with physically finite limits. This creates a severe choke point. While our long-term memory has a functionally infinite capacity to store information, the gateway to get it there can only handle a few elements at once. We often misdiagnose why a learner fails to grasp a concept. Instructional breakdown essentially occurs when the volume of incoming data exceeds the hard processing limits of the system. We measure the burden placed on working memory using a metric called cognitive load. This load is divided into distinct, additive categories that both draw from the exact same finite pool of mental resources. By treating learning as a systems engineering problem, we can manipulate these variables to align instructional material with the brain's physical limits. To calculate cognitive load, we must isolate the foundational unit of learning, which we call an element. An element is any single piece of information, schema, or symbol that needs to be processed. The total number of elements does not dictate the load on working memory. The primary variable is element interactivity. Element interactivity measures the degree to which different elements must be processed simultaneously because they are logically dependent on one another. This diagram compares a memorization task against a procedural logic task. On the left, a chemistry student learning symbols. On the right, a student solving a basic algebra equation. Memorizing chemical symbols has very low element interactivity. Learning that Cu stands for copper does not require you to hold Fe or iron in your mind at the same time. Memorizing 1,000 vocabulary words is time-consuming, but the cognitive load remains low because each element is processed in isolation. Now look at the algebra equation. The division symbol holds no meaning here in isolation. To understand its function, the learner must simultaneously process the division symbol, the variable c, the numerator a plus b, and the result d. This mandatory simultaneous processing of interacting elements creates a heavy demand that rapidly hits the capacity limit of the system. Task difficulty is often a byproduct of volume, but cognitive system failure is caused by the invisible structural web of element interactivity. This baseline burden, created purely by the material's inherent element interactivity, is called intrinsic cognitive load. For any specific task and a learner's given level of prior knowledge, the intrinsic load is completely fixed. We can see how the cognitive system handles this fixed load using primary school multiplication. A student can quickly memorize the string 3 times 4 equals 12. This is rote learning, a mechanical coping strategy that allows the system to process elements in isolation when it cannot handle higher interactivity. Understanding requires linking that fact to a new string, 4 plus 4 plus 4 equals 12, then connecting both to the commutative law. This creates a multi-layered lattice of interconnected nodes that pushes the processing gate to its absolute physical limit. In mechanical terms, understanding is the successful simultaneous processing of this entire interactive lattice in working memory. Connecting these interacting elements together dramatically increases the intrinsic load. When intrinsic load exceeds capacity, the brain naturally severs those connections and defaults back to rote learning just to survive the lesson. Demanding understanding without accounting for the massive intrinsic load it requires is a direct path to catastrophic cognitive failure. While intrinsic load is inherent to the subject, extraneous cognitive load is a separate burden imposed by how information is presented. We must also distinguish between the load itself and germane resources, the mental capacity actually used to process that load. Think of your working memory as a cylinder. The bottom half is filled with the intrinsic load of the material you are trying to learn. The resources currently handling that intrinsic load are what we call germane resources. Poor teaching methods drop a jagged block of extraneous load into that cylinder, causing the mental resources to overflow. Because intrinsic and extraneous load are strictly additive, they compete for the exact same pool of resources. We see this when a novice solves a new math problem using a means-end strategy, searching for the solution path on their own. The student must track the current state, the goal state, and available rules all at once. This creates massive interactivity that has nothing to do with the actual math concept. This extraneous burden crowds out germane resources, leaving the brain with zero capacity to build a lasting schema. When intrinsic load is high, adding extraneous load through poor design guarantees a total system crash. Instructional design brings permanent order to cognitive chaos, leading to schema automation, the collapse of complex elements into a single automated entity. To reach this state, instructors must ruthlessly eliminate extraneous load. Replacing open-ended problem-solving with clear, worked examples removes the artificial burden of searching for a solution. This intervention frees up the maximum amount of germane resources to process the intrinsic load. The tangled web collapses into a single schema and moves into long-term memory. Once stored, this entire complex concept acts as a single element, imposing almost zero load on the system when it is recalled. Effective instruction succeeds by fiercely protecting the finite real estate of working memory until the architecture of understanding is built.